Okay, and welcome to Intermolecular Forces of Attraction for Chem 1. In this unit, we're going to learn about intermolecular forces, which are the attractive forces we talked about briefly in the last unit between gas molecules. But before we get to intermolecular forces, I want to do a little refresher on intramolecular forces, which is what we saw back in chapters 8 and chapter 9. And you may want to go back and review that to just get a better idea of what they are. Intra is a prefix that means within. So these are forces of attraction within molecules or within other substances. And one of the first kinds of intramolecular force is a covalent bond. Covalent bonds are these OH bonds here within the water molecule. And these OH bonds are very strong. They hold the molecules together. So this is what keeps a molecule together. And because they're so strong, it takes a lot of energy to break apart. This would be a decomposition reaction. And a lot of energy means that you need high temperatures, because as we saw in the previous unit, temperature and energy are related to each other. So high temperature and a lot of energy to break apart covalent bonds. Ionic bonds are bonds between positive and negative charges on ions. So if you remember those ions, and these ionic bonds are very strong. As before, it takes a lot of energy to break apart. These charges, they're full charges. And so those full charges are going to be important comparison to what we're going to see later on. It takes a lot of energy to break apart these guys. And in fact, that breaking apart is what we call melting. And because it takes a lot of energy to melt them, all of these guys are solids at room temperature. And finally, for intramolecular forces, we've got metallic bonds. And metallic bonds are the attraction, if you remember, between that metal cation and the negative C of electrons. And those forces can be weaker or stronger than ionic bonds, but they're generally pretty strong. And most metals are solids at room temperature. So that indicates strong bonds. Now, that contrasts to what we call intermolecular forces. Inter, we hear a common prefix in there, inter. Inter means between. So we hear this term in things like interstate, international, intercollegiate. There was another inter I had in mind. You get the idea. Between two things. And the first of these is what we're going to call dipole-dipole or dip-dip forces. We could let you say just dip-dip. These are forces between two dipoles. So we need to have dipoles here. And for right now, we're going to be talking about pure material. So these would be two molecules of the same material. And so we have polar molecules, thinking back to chapter 9, polar molecules. And in those polar molecules where there's an electronegativity difference that's strong enough, and we'll talk about that in a moment, we have an attraction between the partial positive, the delta plus on one molecule, and the delta minus, the partial negative charge, on another. So we have to have partial positives, partial negatives. Now, because I've drawn the pluses and minuses here, I want you to realize in the previous unit, in chapter 9, we were able to draw the dipole arrow. But that dipole arrow is not going to be as useful now because it's not going to tell us where the negative is. So I don't want you to use the arrows now. I want you to stick to the positives, the delta plus and delta minus. Let's take, for example, the molecule hydrogen chloride, HCl, which would be hydrochloric acid if it's in water, but as a gas, and this is a gas at room temperature, HCl is a molecule that's polar because the H and the Cl have a delta En. So remember that delta En difference. And the delta En is big enough here in which the hydrogen has a partial positive and the chlorine has a partial negative. Now, if we take one hydrogen chloride molecule and bring it next to another hydrogen chloride molecule with that same delta plus delta minus, what you can see is that we now have a positive and a negative next to each other, and that red dashed line there, that red dashed line is what we're using to indicate the weaker IMF. The solid black line is the strong covalent bond, and this weak intermolecular force is the red dashed line. Now, for intermolecular forces, dipole-dipoles are medium strength attractions. They're in the middle of the game. I use them first, though, because they're the basis for all other intermolecular forces. So they're medium strength attraction for IMFs, but they're very low overall. And because they're low strength overall, that means that we have low melting points and low boiling points. And these are going to be molecules that are liquids or can be liquids or gases at room temperature. I've developed this little mini periodic table to help us to remember electronegativity and polarity. Now, you can use the polarity chart, or you can kind of get an idea using this mini periodic table at the right. This mini periodic table will get us about 95% of all of our problems, our intermolecular force problems, will be solvable using this chart, this table. Okay, in this little mini periodic table, let's start with row 2. And row 2, we're going to start with carbon. Why carbon? Because it's a nonmetal, and all these guys, all these molecules are nonmetals only. And we have carbon, nitrogen, oxygen, and fluorine. And of course, we're ignoring the noble gases because they don't have any polarity, or they don't form molecules to have any polarity. Now, instead of having other things, now there's nothing above carbon in the normal periodic table, but closely related to carbon in electronegativity, and you'll see why in a moment, is hydrogen. So let's put hydrogen in that row above the carbon. Now, below the carbon in the normal periodic table is silicon, but I'm going to shift sulfur and chlorine over to here. Sulfur below the carbon and chlorine below the nitrogen, because carbon and sulfur have the same electronegativity, and chlorine and nitrogen have the same electronegativity. And what that does is allow me to have elements in the same column. Let me change colors here so that I can demonstrate. So in the same column, form nonpolar bonds because they either have the same electronegativity or close enough that the bond they form is nonpolar. So anything between any two elements in these in a column, so hydrogen, carbon, and sulfur, those form nonpolar bonds between any two of those, and nitrogen and chlorine form nonpolar bond as well. The other direction, horizontally, left to right, we'll have positive, lower electronegativity atoms to the left, and negative, higher electronegativity atoms to the right. So that in any bond between the two of these, in anything between any two atoms, not in the row itself, but left to right, we're going to form polar bonds. A polar covalent bond. And so that can be anything like carbon to nitrogen, nitrogen to fluorine, sulfur to fluorine, anything you can change rows, and that's fine. And so these are going to form polar covalent bonds, and molecules that have them will be able to exhibit dipole-dipole forces. Now, there is an extremely strong dipole-dipole force called a hydrogen bond. So a hydrogen bond is really nothing more than a very strong dipole-dipole force, but it has a very special set of conditions that you need to know about in order to understand when we've got hydrogen bonding. Now, first, a hydrogen bond you can see forms between a small delta plus hydrogen bonded to one molecule. Bonded to either, I got that backwards, bonded to either the nitrogen, oxygen, or fluorine atom, and that would have the negative charge in its one molecule, and that's going to be attracted to the nitrogen, oxygen, or fluorine atom on a second molecule. And I'll show you the demonstration just below. By the way, sometimes NOF, those are in the upper right-hand corner. We'll talk about that. Well, NO and F have the highest electronegativity values, so we can get very big dipoles. And they're also very small, so molecules can get close together. By the way, NO and F, you can turn it around if you want to and say, we're having fun. Hydrogen bonds are fun. They're fun. And this hydrogen bonding explains why water, which would otherwise have a very, very low melting point based on its size or based on the number of electrons, we'll see that down below, would be a gas at room temperature. But because of these hydrogen bonds, it happens to be a liquid at room temperature. So on the left here, I have two water molecules which have been conveniently placed to show the hydrogen bonding between them. And so if we draw in the partial charges, the delta plus, okay, that's not going to work. Let's see if that works. Delta plus, delta plus, delta plus, delta plus on the hydrogens, delta minus, and delta minus on the oxygens. So you can see that those red dashed lines now are the hydrogen bonds. And the hydrogen bond, just to show you, there's that hydrogen atom, and the hydrogen is bonded to one oxygen. So it's bonded to the oxygen. Oh, that didn't work right. Let me try that again. So it's bonded to one oxygen, and it's attracted to the oxygen on the other molecule. We could do the same thing on this one. The hydrogen on one is bonded to the oxygen on the other. And so those hydrogen bonds are the intermolecular forces, those strong intermolecular forces. Now, these intermolecular forces work only for molecules in which the hydrogen is directly bonded to an NO or F. Having fluorine, oxygen, or nitrogen on other molecules, by the way, HF and ammonia with NH bonds also work. Having carbon tetrafluoride with carbon and fluorine bonds to the right here, if we draw the partial negatives and partial positives, we do see that there are these strong polar bonds. Carbon-fluorine bonds are polar. But overall, this molecule is symmetric. And if you remember Chapter 9, that means that the molecule is nonpolar overall. And so this does not exhibit hydrogen bonding. Likewise, difluoromethane on the right. The hydrogen is not bonded to an F. The hydrogen is bonded to the carbon, and these carbon-hydrogen bonds are always nonpolar covalent. Remember, there's no dipole, so don't draw in any dipole on these. But if we put in the partial negatives and the partial positive for the other atoms in the molecule, you do see that this is a polar molecule. And if we were to, say, draw an inverted difluoromethane here and have our partial negatives on the fluorine and the partial positive on the carbon, we can draw in there a dipole-dipole attraction. And so this molecule does exist dipole-dipole attraction between two molecules of that type. So what about nonpolar molecules? Nonpolar molecules have a unique way of forming those dipoles. Now, a thing about nonpolar molecules, they form what are called London dispersion forces. Sometimes we just say dispersion. The word London is not for the city, but for a scientist named London who described these guys. These are present in all materials. So they're present in all materials because, as we'll see, they depend on the electrons. But they're only important when there's nothing stronger. They're only important for nonpolar molecules, and we can also throw atoms in there as well, like for noble gases, which we'll see down below. Nonpolar molecules with no permanent dipoles. So without permanent dipoles, then you can't have a dipole-dipole or hydrogen bonding. So this is going to be the only thing available to you. These are very weak interactions. This is what we call induced dipoles. We'll see in a moment. They're small and they're temporary, and they occur as electrons in the atom or molecule become temporarily unevenly distributed. So I'm going to illustrate below how a dipole can form and how London dispersion forces form. So starting with our nitrogen atom here, nitrogen molecule. Nitrogen is a nonpolar molecule, and as such it has, as on the left, on an even distribution, so nonpolar, and the electrons are evenly distributed. And so there's no dipole on it. But as those electrons are whizzing around that molecule, what can happen is the electrons become unevenly distributed, just temporarily. And so I've indicated by the shading, dark green means more electrons, so that's a partial negative. Lighter green means fewer electrons, and we get the partial positive as that nucleus is sneaking through. Okay, now what's going to happen? Let's bring that molecule down here. So this molecule down here is that same molecule. And let's draw in the partial positive and partial negative that we had before. And again, the uneven distribution. So uneven, I'll just write in uneven electrons here. Now, let's bring up a second molecule. This is our second nitrogen molecule. And bring it next to the first one. And notice what's going to happen. We have that negative charge there is going to push those electrons here. The electrons are going to move away from the first one. And so what's going to happen is that second molecule is again having the electrons become unevenly distributed. Oh, by the way, up here, this first dipole is called an instantaneous dipole because it just happens randomly. Down here now, this is called an induced dipole because it's caused by another dipole happening. So what's going to happen now is, let's go back to red. We've got the partial positive. We're going to bring everything down here again, partial negative. Now, this forms a partial positive and a partial negative because the electrons are going to leave less electrons here, and there are going to be more electrons over here on the right. And now we got a molecule or two molecules where we got a partial negative, partial positive next to each other. We've got our dipole, our instantaneous dipole. And we have our induced dipole on the right. And we have a positive next to a negative. And so we get this very, very small intermolecular force of attraction. In fact, it's so small and it's so weak that for nitrogen molecules, the boiling point is 77 Kelvin, negative 196 degrees Celsius, which tells us that the intermolecular forces here are very weak. Now, the strength of the attraction depends on something called polarizability. This is a fancy word, and all that it means is the ability of electrons to polarize or to form dipoles. So the easier it is to form a dipole, the more polarizable it is. High polarizability equals easy to form dipoles. And this polarizability depends on how many electrons you have. More electrons, and that's usually going to be for a larger atom or molecule, indicate higher polarizability. I'm going to keep using that word. Higher polarizability, stronger intermolecular force. Again, it's got to be that London dispersion forces, LDFs, and higher melting points and boiling points. So let's take a look at the noble gases now. On the left, we have helium, and we know that helium is very small. It's the smallest atom, if you remember correctly, and it has only 2 electrons. Now, hydrogen molecules have 2 electrons as well, but they're a little bit larger, and they've got some size and some shape to them, so they're not quite as low as helium. So with these 2 electrons, we can only form, I don't know how that happened. We can only form very, very small delta plus and delta minus here. By the way, the delta plus, delta minus, you can draw it the other way with the minuses on the left, and you get the exact same thing we got before. So very low boiling point, 4 Kelvin, negative 269 Kelvin. It has the weakest IMFs of any substance, and in fact is so weak that helium can't be made into a solid at any temperature at normal room pressure, 1 atmospheric pressure. Now compare that to argon. Argon, also noble gas, is a much larger molecule and has a whopping 18 electrons, even more than nitrogen. And those 18 electrons mean that we get a much larger positive and negative possible here, much larger temporary dipoles. That should be negative forming. And because the larger IMFs, it has a much higher boiling point. In fact, it's 100 degrees higher, 104 Kelvin, or only minus 169 degrees Celsius. And notice that it is higher than nitrogen temperature, and it does have more electrons than nitrogen. Nitrogen has 14, and argon has 18 electrons. Now, we can apply this to other molecules, things that we call hydrocarbons, such as methane and hexane, with only CH and CC bonds. These are both non-polar covalent molecules. And so they only exhibit London dispersion forces. So we only get those London dispersion forces. And so no polarity in here. So everything's going to depend on the size and number of electrons. Methane on the left is a small molecule with low interaction area. So you can see up above that there's not a lot of place where this nearly spherical molecule can interact. It also has only 10 electrons, and so it has a boiling point of negative 161 degrees Celsius. And what is that? 161, 273, 112 Kelvin. Slightly higher than even argon. And it's a gas at room temperature. On the right, with hexane, hexane is larger. And it has more interaction area. This is like Velcro. More interaction area. Where if we have a larger piece of Velcro, it's going to stick together stronger because it just has more things holding it together. It also has 50 electrons, so a lot more electrons, and its boiling point is a whopping 69, positive 69, let's put that in there, degrees Celsius, or add 273, 342 Kelvin, if I've done my math right. And because of that, it's a liquid at room temperature. So to review with hexane, hexane has more interactions. It has more electrons. So it has stronger IMFs and higher boiling point. Okay, for the homework for this, you are first you're going to read the also included article, or actually a section from another textbook on intermolecular forces that might help you understand them a little bit better. And then the attached worksheet will also be for your homework. All right, I will see you in class, and have a good day.